So we're recording. So welcome everyone to today's fluid dynamics seminar. It's a great pleasure to have with us John Bush, an old friend and colleague, and who's doing incredibly interesting things. And he's been working on this quantum analogy in fluid mechanics for a few years, and he's going to tell us all about it. So John, whenever you're ready.
Very good. Here we go. Host disabled participant screen sharing.
Okay, let me make you co-host. Sorry, I should have done that before. Yeah, should be okay now.
Okay. Are we there?
Yes, it's all good.
Okay, so yes, so I'll be talking today about the sort of full range of this problem. So starting with experimental fluid mechanics all the way up to some slightly more speculative formulations of quantum theory with dynamics. And so, wow, what happened there? Okay, so I should start by thanking the many people who've been contributors. Dimitri mentioned I've been working on this problem now for over 10 years. So you introduced me to the problem and sort of been running with it. Dan Harris was critical in getting the experimental program going. Pedro Sainz was really the driving force in the lab since then. And it's, I think, a testament to the richness of the problem that so many people have profitably worked on this problem. And again, many of my former grad students are now faculty, so Anand and Dan, and my postdocs are now collaborators with faculty positions. So I'd like to thank them all for their many contributions. And we have an interesting feature here. My arrow button doesn't work, but that's okay. Okay, so what is quantum mechanics? It's a theory that describes the statistics of microscopic particles, but it does not describe the trajectory. So their description of the free particle, which one can find very frustrating as an undergraduate, is simply that there is a vibration associated with the particle. So you characterize its energy in terms of h bar omega and its momentum in terms of a wave number. Okay, so you're really associating a particle with the wave, but where is the particle and why does it move? Okay, so one, of course, would like to have a trajectory equation and then see how that dynamics can be reconciled with the statistical theory. And the fact that they, if one actually insists that the theory is complete, that there are no such trajectories, then one is faced with all sorts of difficulties which have been around for almost a century. In particular, the proliferation of quantum interpretations and troubling language and paradoxes. So some examples of the language here. So wave particle duality, uncertainty, complementarity, spin. This is now a non-classical internal angular momentum. One has superposition, non-locality, wave function collapse, non-local quantum potential in Bohmian mechanics, and there's single particle diffraction interference and entanglement. So this grocery list of troubling language, this bouncing drop system really provides a physical picture which allows you to try and understand it. So of course we aren't all the way there. We can't tell you what entanglement is just yet, but the theory is progressive. So let's move on. So what are hidden variable theories? These are theories that would seek an underlying dynamics that would describe the particle trajectories, and these trajectories would be consistent with the statistical predictions of quantum theory. So all of the existing hidden variable theories involve a pilot wave dynamics in which a particle is guided by a wave. So the first such theory was proposed by de Broglie in the 1920s. So he imagined a particle as a source of its own wave field moving in resonance with a guiding wave. And then again, this pilot wave dynamics gives rise to a statistical behavior which is consistent with standard prediction. So Bohmian mechanics is a little more simplified, and I think overly simplified. So here you basically have a particle being guided by a statistical wave, but we'll come to that a little later. And then Nelson's stochastic dynamics imagined a particle interacting with a stochastic background field. And this has been so that there's an effective diffusivity, which is related to the particle speed times the de Broglie wavelength. And this has been pushed forward in the context of stochastic electrodynamics. So Tilapeni and Chetto have a theory in which the pilot wave is sought in the electromagnetic quantum vacuum. Okay, so now, so fast forward to 2005, and Yves Couder and Emmanuel Faure discovered this hydrodynamic system in which a particle moves in resonance with a guiding wave. So it's really a realization of de Broglie's mechanics, as we'll see. And this, lo and behold, it exhibits several features of quantum systems that are thought to be exclusive to the microscopic realm. Okay, so the questions that one is obviously inclined to ask are, what are the key features of this hydrodynamic system responsible for the quantum-like behavior? What are its, what's its potential and what are its limitations as a quantum analog? And can it guide us towards a rational theory for quantum dynamics? So the first question is effectively answered. We're still exploring the second and the third, and I'll give you an update on our thinking along those lines. Okay, so we'll start off talking about the hydrodynamic system and the various analogs and how we describe the system theoretically. So that's basically the first component is experimental, the next is theoretical, and then it suggests, so we know that we want to sort of broaden the scope of dynamical systems we look at. So we will capture the essential features of the hydrodynamic system and then develop a sort of generalized pilot wave framework. And this then touches on existing quantum pilot wave theory. So it sort of provides a bridge between the macroscopic dynamics of the walking droplets and the microscopic the theory proposed for microscopic particles in the 20s and the 50s by de Broglie and Bohm. Okay, and so the hydrodynamic system you've probably all seen at some stage, but it's so you have a vibrating bath of fluid, you're driving around 50 hertz, and at a critical, so the vibrational acceleration is the amplitude times the frequency squared. So when that exceeds a critical value relative to gravity, you excite a standing field of subharmonic waves. That is to say, they have twice the period, half the frequency of the vibrational forcing. Okay, so you can levitate a drop on the surface of a vibrating bath. This was shown by Gerald Walker in the 70s. And it will, of course, emit a field of waves. So note that all of the experiments which we're describing here take place below the Faraday threshold. So the there would be no waves in the absence of the drop. Okay, so we never actually cross the Faraday threshold. Nevertheless, the drop generates a wave field, and it's this wave field which destabilizes it at a critical vibrational acceleration. So this drop you can see is moving very slowly from left to right, and it's because it's landing on the slope of its wave field. Okay, so each time it strikes, it gets a little push. Okay, and there is actually a resonance between the drop and the wave. So the drop is bouncing at the Faraday period. And the key feature of the system is that it's non-Markovian. That is to say, in order to, the force acting on the drop locally is determined by the slope of the bath, and in order to calculate that slope, you have to integrate back in time because there are contributions to the shape of the interface from all of the previous bounces. And the closer you are to the threshold, the more persistent the waves are, and so the longer you have to integrate back in time. So we call this the memory of the system. So it's sort of like a dynamical system with a delay. So you basically have to integrate backwards in time. Okay, and it's this path memory which is really the key feature responsible for all of the quantum-like behavior in the system. Okay, so here's the trajectory equation. Here you can see how the memory comes in. So you have the mass times acceleration. You have a drag, which depends on that induced during flight and during impact. And then you have the wave field. And the wave field, in order to calculate, you have to basically you have a discrete sum going backwards in time. Every time the thing hits, it basically lays down a Bessel function with some spatio-temporal damping. Okay, and you see the memory parameter now appears explicitly here. It appears in the exponent of the wave field. And so as the memory becomes large, that is to say, as gamma, the vibrational acceleration, approaches the Faraday threshold, this thing, the memory gets very large, and you have to integrate back in time for a very long time. Okay, so that is to say, it's influenced by its past. Okay, and so we can also strobe the dynamics. So instead of having the thing bouncing up and down, we can just grab 1 frame per bounce and the thing just glides along. So you see this here very clearly, the resonance between the particle and the bath. And here the particle is effectively surfing on the interface, dressed by this quasi-monochromatic pilot wave field, whose wavelength is the Faraday wavelength. Okay, and so we can also describe that dynamic. So we can now we basically just time average over the vertical dynamics, and so get this stroboscopic model, which was developed by Anand Oza during his PhD. So here we, instead of the discrete sum, we have an integral over time to calculate the slope of the wave field. And so we then have an integral differential equation, which is amenable to analysis. So you can assess the stability of various states. So the transition from bouncing to walking and various other states, as we'll see in a moment. And so these, we can have static bounce states. So they'll basically lock into an array, a square array. You can have pairs, trios, or a square array. Triangular array. These are some problems that Miles Couchman has been looking at recently. And so dynamic, and we can also have dynamic bound states. So these drops can become, the walking drops can lock into orbit or walk side by side, promenading pairs, which seem to behave like vortex pairs in certain regards. And we can also have rings of bouncing drops. So this is work done by Miles during his PhD. So here we start off with a free circular ring of drops, and you see the instability set in here, and you have these rather exotic shapes forming down at the bottom. You get irregular polygons emerging, and this is an experiment done by Stuart Thompson, where you have particles in a circular array. So if they're limited, their radial motion is confined, and so you get these sort of solitons zipping around the ring. So these are all things which we've looked at and rationalized theoretically and forged some sort of nice links with solid state physics. Okay, so in terms of quantum analogs, the first such experiment was done by Couder in 2005, and he had the brilliant idea to send a walker towards a slit. Okay, so I know that if I had discovered the walking droplet, I would have analyzed it and understood it, but I wouldn't have thought to taken this step. So I think it was a sort of a landmark paper. So he sent the walker towards a slit, and he measured the diffraction pattern. So this is the number of drops deflected as a function of angle. Okay, so you see this sort of 3-peak structure, which is quite robust. And they found that in the double slit experiment, the drop is influenced by the second slit by virtue of the fact that its pilot wave extends across both. Okay, and this is of course one of the many inscrutable things in quantum mechanics, as insisted upon by Feynman in his textbooks. And we went back and revisited this experiment, and these have been done even more recently by a group in Denmark. And these are all sort of internally consistent. We get this 3-lobe structure, but the details of the diffraction patterns are different from those in quantum mechanics. So sure, we get some wave-like form, but it's not a Fraunhofer diffraction pattern. But why would it be? So Fraunhofer diffraction pattern, it relies on the wavelength of the particle being very small relative to the slit size, and it certainly isn't in our experiments. But we do have this key feature, which is that the particle, so here we have a particle going, these slits are identical, but here there's a second slit, and you can see that the particle is deflected when there's a second slit in a way that it isn't when there's only a single slit. And so this is clear indication that the pattern is altered by the presence of the second slit. And so you could say, well, that's non-locality, but it's really not. It's just because the walker, so the walker we now have to think of as the particle and this wave that it's dressed in, and that interacts with both slits. Okay. And so what we'll see, actually, when we get to the end of the talk, we're going to have this sort of hydrodynamically inspired quantum field theory. And here we're going to see that the wave form that one would expect in quantum mechanics is quite different from that arising here. In particular, it's a plane wave. And because it's a plane wave, you expect the diffraction to perhaps be more like what one sees in quantum mechanics. Okay. And again, it's good that you get a wave form. It's good that in terms of the diffraction pattern, it's good that you get this non-local effect of the second slit, but the details are different. But well, that's hardly surprising given how different the systems are. Okay. Okay, and so the second very robust analog was this walkers in a rotating frame. So from your classical mechanics class, you know that if an object moves in a rotating frame, you expect it to execute an inertial orbit where there's a balance between centripetal outwards force and an inwards Coriolis force. So one expects then if the particle is moving at uniform speed v, then its orbital radius should decrease like 1 over omega. And that's what happens in the Walker system. So they did experiments with a rotating bath. So the particle executes a circular orbit, and whose radius decreases with rotation rate. But at high memory, the drop starts interacting with its own wave field. So it's basically feeling its own wake. So it's now navigating this corrugated surface, which is centered on its orbital center. And so the orbital radii become quantized, and they're quantized on this Faraday wavelength. Okay, so they're a discrete set of possible circular orbits which are accessible. And so you see this emergence of quantization here. So there's a preference for discrete orbits. And given the analogy between the Coriolis force acting on a mass m in a uniformly rotating fluid and the Lorentz force acting on a charge q in a uniform magnetic field, they drew the analogy between these quantized Couder levels and Larmor levels. And again, so, and we see that the Faraday wavelength is playing the role of the de Broglie wavelength. Okay, and so we went back and we examined this problem both theoretically and experimentally. So theoretically, we can just take our stroboscopic model and add a Coriolis force, and so we can seek orbital solutions and assess their stability. Okay, and so doing so gives us this curve. So this is the radius of curvature. So at sort of mid-memory, you have these portions of the solution curve which are unstable, and these are experiments done by Dan Harris. And you can see, so we only get orbital solutions along the stable branches of the curve. And then as the memory increases, the solution curve, more and more of it is unstable. So the green parts of the curve correspond to unstable eigenvalues with an imaginary component. So you expect the thing to wobble as it blows up. But as you go to higher and higher memory, things become more and more unstable. And so what happens when the system becomes chaotic? So here's a stable circular orbit. If you increase the memory just a little bit, it jumps between discrete quantized orbits. So it's chaotic, but there is still this preference for certain quantized orbits. And so if you plot the radius of curvature as a function of time, again, you have these plateaus. So it's sort of jumping between these unstable circular orbits. And so you get a sort of multimodal statistical behavior, so which reflects the preference for these unstable circular orbits. Okay, and this is sort of a classic. So this is the first sort of physical picture of how quantum-like statistics can emerge from this pilot wave system. And an interesting feature that we'll come back to is that from this rotating case, the solution curve actually touches down on axis. And so the axis is the omega equals 0 axis. So it's saying that it's possible theoretically to have a drop zipping around in its own wave field, even in the absence of a Coriolis force. And so in order for that to happen, you have to have the inertial force balanced by the wave force. Okay, so it turns out these are all unstable. We would call these hydrodynamic spin states. These are unstable in the lab, but we'll see that you can stabilize them in a generalized pilot wave framework. And there's actually something analogous to Zeeman splitting as well, if you apply weak rotation to these so-called spin states. So, and so this physical picture of which emerges from these studies of orbital pilot wave dynamics is also manifest here. So here, this is a drop moving in a central potential. So it's basically a drop in a spring force. So these are experiments done by Stéphane Perard, who is in Yu's group. And they found that when you have such motion, the drop, of course, drops always want to move walk in a straight line, but they're being confined by the spring potential, so they sweep back. And so you get the solutions, you get circles, lemniscates, sort of dog bone, and then more elaborate orbital forms. And these forms are quantized in terms of both mean radius, which is like the a proxy for energy, and the mean angular momentum. And so here we see you see circular orbits of different radii, and then you see along the zero angular momentum line, you get these lemniscates, and then you get more elaborate orbital forms. And again, when the system becomes chaotic, the Walker switches between accessible periodic orbits. Okay, so you then get, again, chaotic trajectories with multimodal statistics. Okay. And so my entree into this problem was the following. So these are experiments done on the quantum scale. This is so-called quantum corral. So here you have electrons zipping around inside a corral. So the scale is 75 angstroms, and the fence on the corral are these positive atoms which repel the electrons. So the electrons are basically rattling around, and this is actually the measured voltage, which is an indication. It basically tells you what the wave function is. So it's giving you the probability of presence. And so you see this wave-like structure with the de Broglie wavelength, okay? And so I thought, well, this is pretty exciting. What Yves done is this actually going to work? And this is an experiment which Dan Harris did during his PhD, and when I saw that this worked, I pushed all my chips in and said, okay, let's go for this. And so so you see the drop wandering around. Its trajectory is color-coded according to speed, and you think, this is a mess. Nothing is going to emerge. But sure enough, in the fullness of time, you see there's a correlation between position and speed. And as a result, there's an emergent statistical form, which is really very similar to that emerging in the quantum corral. And here we see that the wavelength is now, of course, the Faraday wavelength. So we see that this Faraday wavelength is always playing the role of the de Broglie wavelength so far in everything we've seen. Okay, so we see the emergence of this coherent wave-like statistics from chaotic pilot wave dynamics. And so the sort of physical picture you get is that you have this high frequency vibration, in particular the drop bouncing, which gives rise to the wave. The wave pushes the particle around. Then you have this intermediate time scale, which is the time scale of basically convection, so the time scale of the drop motion. And then you have this long-term statistical behavior. So on the long time scale, you see this emergent statistically steady form. And it's quite remarkable that when you consider this is a fraction of a second, right? The bouncing, so it's bouncing at 50 hertz. And the thing's walking around 1 centimeter per second. I should mention these drops are about a millimeter in scale. But so the time scale for the emergence of the statistically steady form is around an hour. So again, given the difference in scale, so this is again, this corral is on sort of centimeter scale, and we've gone from the angstrom scale. So it's quite remarkable that by jumping in scale from up to the quantum, we're actually able to characterize all three of these timescales in the lab. So it was a sort of a very happy coincidence. Okay, and so we've also looked at motion in an elliptical corral, and this is there's a number of, we sort of get a mixing of statistical modes there, and so Pedro Sain showed that we can get a sort of a statistical projection effect. But the thing I want to stress here is slightly different. So here again we see there's a correlation between position and speed, which gives rise to emergent statistical form. But what we see is that this emergent statistical form takes the same form as the average wave field. So if we look at the wave field at any given instant, top left, it's a bit of a mess, but if you time average it, it basically corresponds to a superposition of two different modes, okay? But remarkably, the average wave field basically takes the form of the particle histogram, okay? Which is interesting. And so this led Matt Dury to the following result. So if you, so the mean pilot wave, he showed that the mean pilot wave is given by the convolution of the histogram of the particle and the wave field of the bouncer. Okay, so this is the wave field, the wave field of a drop if it's bouncing in place, described here. And of course, its form is going to depend on memory. But it's kind of a nice result. And you have this notion then of the particle navigating a potential of its own creation, which is this mean pilot wave potential. Okay, and again, it's a strange potential because it actually depends on the statistics of the system, and we'll see that this is analogous to the quantum potential in Bohmian mechanics. Okay, and so in a 1D motion, so here's a drop moving back and forth along a line, and at relatively low memory, so the instantaneous wave field is different from the mean. But as you go to very, very high memory, the two converge. So here, when the memory is sort of moderate, this is the mean pilot wave is indicated in black, and the instantaneous pilot wave is in blue. And you can see it sort of follows the drop and rattles around. But as you get to very high memory, this background mean pilot wave potential is basically fixed, and and that's what the drop is navigating. So, and given that it depends on the statistics of the particle, you can see that it's basically a non-local potential. It appears to be a non-local potential, where of course the dynamics is entirely local. Okay, so here's another beguiling problem, which I think Darren Crowdy was the second to be aware of, because we discussed it down in Rio. So we're looking at scattering, and you'd think, okay, I just wanted to try and understand how walkers interact with boundaries. I said, well, what happens if it hits a pillar? And we thought, well, it's just going to scatter, right? That's kind of what we expected. But as with everything with this problem, it's always much richer than you expect. And actually what happens is the drop is deflected along a spiral. So this is a submerged pillar, and these are surface shearing, so you can see what the wave field is. And it's not just any spiral, it's a log spiral. So the drop comes in, and it's deflected and follows this logarithmic spiral. And so from the form of the spiral, you can infer so we're going to play a game. Let's imagine we don't know that it's pilot wave dynamics, and let's just infer the effective force that would be necessary to give rise to this spiral. Okay. And so what is that force? It's actually a lift force. So it's proportional to this boosted mass, and I won't go into details there, but there's basically a wave-induced added mass, and it's proportional to the particle velocity crossed its instantaneous angular velocity around the pillar. Okay, so it's a very beguiling result. So especially given the, again, identical forms of the Coriolis force and the Lorentz force, it looks like a charge responding to the magnetic field generated by its own motion, right? So it's basically, you consider its motion as being a current. This gives rise to a magnetic field. So it sort of looks like hydrodynamic self-induction. I think there's something deep here, which I'm afraid I don't understand yet, but I'm hoping some of you will help me to understand it. So, but most importantly, whatever form this takes, again, the fact that it's exactly, you get a factor of 2 pi, like there's no, and the boosted mass, it looks exactly like Coriolis force is beguiling. But whatever the form of the force was, you can see that if you deny the fact that it's a pilot wave system, we know that the real reason it's being deflected is because its pilot wave is being altered by the presence of the pillar. So you basically have these wave mediated forces giving rise to what appear to be non-local forces, and here it's a lift force. Okay, so again, you see the way that non-local forces can appear to arise in this because by virtue of the pilot wave dynamics. Okay, and Friedel oscillation. So this is a recent study, a favorite, which we did with Pedro Sainz, and this is a model. So the Friedel oscillations in quantum mechanics is the same sort of system as the Corral. You basically have a liquid metal, and you have an electron C zipping around on it, and where you have irregularities, you have the electrons scatter off them, and you get these rings in the PDF. And so there's no interaction mechanism because they don't have a trajectory equation, so they just model these as scattering potentials. Okay, so can we get the same thing with the walking drops? And so here we see a walker approaching the well. So it's now, instead of having a pillar as we did in the last experiment, we have a well, and the thing is drawn inwards and sweeps through the center of the well. And so again, you have some wave mediated lift force generated, which drags the thing here along an Archimedean spiral inwards towards the well. And you let the thing run. So these are experiments, and we again color code trajectories according to speed. And as you let the thing run and run, so they're basically inline oscillations generated as the thing passes through the well center. And so ultimately you get this statistical signature, which is very much like Friedel oscillations, okay? And it's basically rooted in these inline oscillations excited when the walker interacts with the well. So really, this is, you know, down to the sort of magnitude of the disturbance in the PDF. This is really very strongly reminiscent of Friedel oscillations, from which one can make the most conservative conclusion that Friedel oscillations are not inconsistent with the notion of electron trajectories. Okay, so there's sort of three paradigms. I've only gone into two so far, but for the emergence of quantum behavior from this macroscopic system, and all of them depend critically on the resonance between the drop and the wave. And this is what's responsible for the quasi-monochromatic wave field with the Faraday wavelength. And then they have the these quantized states emerge by virtue of the dynamic constraint imposed by this monochromatic wave field, okay? And so we've seen in the orbital dynamics that you get this chaotic switching between these unstable orbital solutions, which gives rise to multimodal quantum-like statistics. And then we've just seen in the Friedel oscillations, these inline oscillations can also give rise to a statistical signature with the wavelength of the pilot wave. And then there's also a regime, which we'll see a little more of here, where the inline motion becomes unstable and you get this random walk, and the diffusivity looks like the particle speed times the wavelength of the pilot wave. So we'll see this when we move into a generalized pilot wave framework. Okay, so now there's a growing list of hydrodynamic quantum analogs, and I certainly don't have time to discuss all of them here. I've just discussed some of my favorites, but you can learn more on my webpage and elsewhere. But so these work to various degrees of success, and when they work, it's of course very satisfying. When they don't, we have to think harder and think about what needs to change. And so one thing that's clear, you know, a limitation of the system comes, you know, all of the quantum-like features emerge at high memory. That is to say, when the waves are weakly damped. So viscous damping is our enemy here. We want to move to the regime where there's very high memory and low viscous damping, and also drop inertia can be problematic. In particular, these spin states are unstable in the lab by virtue of the drop inertia. So, but let's now again we sort of let our minds wander and imagine a broader class of dynamical systems. Okay, so this is we call it a generalized pilot wave framework, where we retain the key features of the Walker system, but explore beyond the range of the hydrodynamic system. And this is going to allow us, as we'll see, to connect to quantum pilot wave theories and start making up our own. Okay, so here's the non-dimensionalized stroboscopic model. So we non-dimensionalize this. There are three terms, so they're going to be two dimensionless groups. These are basically gamma, which is the proximity to threshold. So that's the basically how close you are to the Faraday threshold. So that sets how long the waves last. And then we have this kappa naught parameter, which is the basically prescribes the inertia of the particle. Okay, and so this, notice, has all of the fluid parameters in it. And in the lab, it's restricted to the range 0.8 to 1.6. But what happens if that parameter is 10 to the minus 6? What happens if it's 10 to the 14? Or can we capture other features which are reminiscent of quantum systems? Okay, so for example, when are hydrodynamic spin states stable? When is the walking state unstable to these inline oscillations, which we've seen can give rise to quantum-like statistics? So we can answer those questions. So Anand Oza looked at this. So you can basically see where we saw that these spin states are unstable in the lab, But if you go to the limit of small drop inertia, you can basically stabilize these spin states. Okay, so you then have a drop zipping around its own wave field, its inertial force balanced by the wave force. Okay, and so most recently, this paper just came out today, actually, with Matt Dury. So here we do tile the entire plane of this generalized pilot wave framework. So here's again basically the longevity of the wave field, and here is the particle inertia, and so you get these different regimes. So the bottom, in the bottom region here, this sort of teal, you have linear rectilinear motion and overdamped oscillation. So if you perturb it, the thing will quickly go back to its free walking speed. Here in the baby blue region, you get underdamped oscillation. So you can get some signatures such as we saw in the Friedel oscillations. And then there's a region happening at very high memory where this thing becomes unstable and you get this random walk which is characterized in terms of diffusivity, which is proportional to the particle speed times the Faraday wavelength. Okay, so this is again something one doesn't see in the lab, but one can see in this generalized framework and has been reported elsewhere by some of the French researchers using their theoretical model. And so, and we also discovered that there are these sort of more exotic spin states. So near the spin region, we have these wobbling and precessing orbits. Okay, and so, but we can imagine further generalizations. So one can, for example, consider alternative waveforms, spatiotemporal damping. We're now extending this sort of theoretical framework to 3D. So now you imagine a particle emitting spherically symmetric waves, and then at a critical wave amplitude, it will become unstable and start moving. So we're currently exploring this. And then you can also imagine some stochastic forcing. So you have some sort of hybrid pilot wave stochastic dynamics. And also this connects, as we'll see, allows us to connect to the early pilot wave theories. Okay, so the old hydrodynamic interpretation of quantum mechanics is due to Madlung. So he said, okay, let's take the wave function and execute this polar transformation. So rho is now the probability density, S is the action. And if you do so, the real and imaginary parts take a hydrodynamic form. So you have basically, this is the continuity of probability. And then you have this term here, which they call the quantum Hamilton-Jacobi, though it's a description really of statistics. And you have this quantum potential term arising. And notice that this is a curvature term. If you linearize around nearly constant rho, then it looks like a curvature term. You're going to act to flatten out variations in probability by an amount prescribed by h bar. Okay, so it's kind of nice. Note that h bar, which appears in 2 of the 3 terms here, only appears here once you do this Madlung transformation, and it's basically in front of a curvature term. Okay, so but this is just describing the statistics. So it's a way to interpret. There's no sense of trajectory here. It's just telling you how to think in terms of the evolution of the statistics of a quantum system hydrodynamically. So U is not the particle speed, it's the quantum velocity of probability. Okay. So Bohm said, okay, well, let's try and make a dynamical theory out of the Schrodinger equation. So he said, okay, let's set this particle velocity equal to the quantum velocity of probability. Of course, you expect it to be true if it's describing an average dynamics, which I think it is. But he said, okay, this will then be the trajectory equation. So the particle then moves in response to this non-local quantum potential, which we've just defined here, and whatever classical potential might be around. And so this is problematic in that you have a non-local quantum potential whose form is, of course, deduced from the wave function. So you have a non-local potential that's determined by the statistics of the system. And hopefully this will be ringing bells from what I said previously about our mean pilot wave potential. Okay, so it has some problems, and so that were pointed out by Einstein and others, including Joe Keller. And so he then subsequently invoked he says, okay, we have to have some stochastic background to get around these difficulties. So let's throw in, let's appeal to the quantum vacuum and have some stochastic forcing to augment our trajectory equations. Okay, so if you do this, it's kind of interesting to compare his dynamics to ours. So his dynamics, so he's basically, he has this guidance equation, which has a non-local potential plus an ad hoc stochastic forcing. Ours is local. We have a local potential, which is the slope of the wave, but we've seen that we can decompose this into a mean wave field, which is non-local, and a perturbation wave field, right? So we can see how the difficulties he had, that being the non-locality, which and this ad hoc stochastic forcing, can be sort of reconciled with a local dynamics, right? So you just have to recognize that the real wave field is local. It's created by the particle, and the mean dynamics will be described by the mean pilot wave potential, which is in their case is the non-local wave potential. Okay, so, and the other frustrating thing about Bohmian mechanics, of course, there's no mechanism for wave generation, right? He just says, okay, let's solve Schrödinger's equation in any given geometry. That gives us the quantum potential. Then we fire a particle and it navigates this potential, right? In our system, we have the notion of the particle being the source of its own wave field and its own potential. Okay, so ours is actually closer in spirit to the original formulation of de Broglie. So I really like this theory because of its simplicity. It says a particle has an internal oscillation. So you can say, well, what's its frequency? Well, relativity tells you that E equals mc squared. Quantum mechanics tells you that E equals h bar omega. And this is the so-called Einstein-de Broglie relation. It defines the Compton frequency, which is mc squared over h bar. De Broglie said that at this frequency, there's an exchange between rest mass energy and field energy. So basically the particle is again a vibrating source of fields, okay? And so his theory is called the double wave solution because there are two waves. There's the wave generated by the particle, and then there's which is responsible for guiding it. And then there's a second wave, which is the statistical wave, which is the standard wave function in quantum mechanics. And so what he didn't show is that how the particle dynamics governed by this wave field psi gives rise to the statistics described, which are required by the correct predictions of standard quantum theory. Okay, and so he really, so this was his physical picture, but he didn't have detail. He didn't see how the particle generated the wave. So he didn't have a model which said how the particle interacts with the wave in order to generate it, right? So it's sort of a physical picture, but from this he got P equals, from his physical picture, he got P equals h bar k, which follows from the fact that if a particle is dressed in a monochromatic wave, the particle has speed has to be equal to the group velocity of the wave packet, right? So that's where P equals h bar k comes from, and that formed the foundations of, that was basically a cornerstone in deriving Schrödinger's equation. Schrödinger derived the equation to describe the pilot wave in de Broglie's mechanics, but it was subsequently pirated for describing the statistics. Okay. In any case, I digress. The other thing he stressed was the resonance between the particle and its guiding wave. Okay, but he did not describe. This is why he stalled. Really, he didn't have a notion, a sort of physical picture of how the particle locally creates the wave. Okay, and so this is the physical picture which has been furnished by the walking droplet, so allows us to move forward a little bit. But you see the physical picture is very similar. So you view this particle as having a high frequency oscillation. Then you had this intermediate pilot wave dynamics with the particle riding its guiding wave in such a way that P equals h bar k. And then you had this long-term emergence of the wave function. Okay, and so the relation between the two. So we have the bouncing drop is playing the role of the zitter. That's what they call the high frequency oscillation. And we have capillary Faraday waves, he had
No.
matter waves, and in Higgs field,
Yeah.
he stressed the wave parameter because we have capillary Faraday waves is surface, and we've seen that the Faraday wavelength is playing a role of the demo. You can see how that is related to the
I think we've lost John there.
Yeah, thanks, Demetrios. I thought it was me.
Oh, no, let's see.
Anybody can see his slides, or everything is gone?
No, I think his internet must be down.
Yeah.
Probably his Zoom is Zoom fatigued.
Yeah, it could be. I hope he realized and he's not just talking.
Yeah.
And I'll send John an email.
Yeah.
Are you with me?
Hi, John, you're back. Yeah, we lost you there.
Where did I disappear?
Let me just...
Now we have to see if anyone was paying attention.
Okay.
Probably it was one of your tricks, John.
The uncertainty principle. Should be co-host.
That's happened before. That was just that's just a Zoom failure, is it?
Who knows? Or internet.
Yeah. So you're with me now?
Yes. Yeah, we're good.
Okay. Yeah. So I was just getting here. So what was wrong with the quantum pilot wave theories? They really don't have this notion of how the particle generates a wave. Okay. This is true for both Bohmian mechanics and de Broglie's mechanics. And so basically, we're now trying to push the boat out and see if we can extend de Broglie's mechanics informed by the pilot wave system. So in Holland's book on Bohmian mechanics, he says the following: we can envisage a more active role for the particle, something which is not even admitted as conceivable in the conventional view. This may, for instance, enter as a source of the pilot wave field through an inhomogeneous term in the wave equation. So that's exactly what we do. So it looks very much like the hydrodynamic system. We now have Klein-Gordon equation as suggested by de Broglie, and which describes the Higgs field, and then we have a localized disturbance at the Compton frequency. And so this is work which is done with Yuval Dagan and more recently by Matt Dury. So we basically have, for the sake of simplicity, we're just having gradient-driven motion. So we're throwing inertia out. We have a coupling constant. So this is sort of consistent with the relativistic guidance equation. Gamma is now the boost factor. So we're basically doing the same dynamics, but now we have all quantum constants in our theory, right? So in kinematics, if the particle is just sitting there vibrating, it generates waves with the Compton wavelength. If it starts moving, you get a waveform where there's a signature of both the de Broglie wavelength and the Compton wavelength, as you see here. So as the de Broglie wavelength approaches the Compton wavelength as the particle speed increases, but you can see it looks very much like the walkers, right? The particles, so this is the walker in the top row. In the bottom rows, you see the result from this hydrodynamic quantum field theory, the particle riding its wave field whose form depends on its speed, okay? So that's kinematics. And we can also look at dynamics. So dynamics is a critical coupling constant at which the thing starts moving. And when it does, it moves such that P equals h bar k. So this is a nice result. Moreover, there are these inline oscillations with the de Broglie wavelength, which are reminiscent of those which we saw in the Friedel oscillation study. Okay, so in fact, you get, if you look at the spectrum of the waves, you see that it satisfies the relativistic dispersion relation in quantum mechanics. So you can now sort of associate this Compton squared omega c squared as being associated with the rest mass, and this c squared k squared is being associated with inline oscillations. Okay, and so, and the other beautiful thing is, so in 2D, this was work done by Matt Dury, the pilot wave field, it no longer has a sort of horseshoe-like form as it does for the Walker, but it takes the form of a plane wave with the de Broglie wavelength. So if we look at diffraction from a slit, for example, that's of course how they solve for the diffraction pattern. They basically look at diffracting plane wave. It's more hopeful, so we're certainly going to get a different form for the diffraction pattern than we do in the Walker system. So this is, we'll revisit the Walker's the diffraction problem in the context of this hydrodynamic quantum field theory. Okay, so and so the other nice thing is there are two wavelengths in relativistic quantum mechanics. There's the de Broglie wavelength and the Compton wavelength. And until recently, I was confused as to what these two wavelengths were, because there's one dominant wavelength in the hydrodynamic system, but it turns out this study shows that non-relativistic quantum dynamics, the Faraday wavelength is playing the role of the de Broglie wavelength, whereas when the speed of the particle approaches the speed of light, the Faraday wavelength should be playing the role of the Compton wavelength, in which case you can expect some structure on that scale. So for example, these spin states, the classical model of the electron is a charge zipping around the Compton wavelength at the speed of light. So we can hope to capture some sort of structure with this hydrodynamic quantum field theory. Okay, and so we're going to basically couple this with the ensemble interpretation of quantum mechanics. So we start with some ensemble of initial conditions, look to see how they evolve and see if they evolve consistently with the predictions of standard quantum theory. So we basically made that quantum leap now. We've gone from the hydrodynamic system to this system where we have de Broglie wavelength, Compton wavelength floating around rather than Faraday wavelength. And so we're looking to see what it yields. So we're going to start with some of the systems with the most robust hydrodynamic quantum analogs, particular Friedel oscillations, Corrals, and we'll do diffraction. And we'll basically be doing what de Broglie would have done if he had had MATLAB and an army of talented grad students and postdocs. Okay, and so we're really at the stage where we can start trying to demystify the quantum language. So a wave-particle duality is really not much of an issue for us. We think there is a particle and a wave, and this is precisely what de Broglie said. Uncertainty this is really rooted in unresolved, we believe that it's rooted in the unresolved dynamics on the Compton scale. Complementarity, so there's some things which are just unnecessary conceits, that being one of them. Spin, we imagine as being a manifestation of angular motion on the Compton scale. Superposition, you have the coexistence of accessible, unstable dynamical states. Non-locality, now this is a big one, right? So we would say that it's a misinference, a manifestation of local hereditary dynamics. And you can see here, so these are three examples of non-locality where one could misinfer non-locality. So for example, in the Corral problem, if you said this statistical form is a complete description of the system, then the active observation causes it to collapse instantaneously to a point, that would be non-local. But of course, we see that it isn't. There is an underlying dynamics. Similarly here, when the Walker interacted with a well and a pillar, we saw these non-local lift forces, but those are simply a manifestation of wave-mediated local forces. So you may make those inferences again if you deny that there's a pilot wave dynamics. Similarly here, there's basically a mean pilot wave potential, and you could misinfer this as being non-local because it involves the statistical form. So it really plays a role analogous to the Bohmian quantum potential. Okay, and wave function collapse, again, it's not a problem for us. Quantum potential, we see the non-local mean pilot wave potential. Single particle interference, we see this is again a manifestation of hereditary pilot wave dynamics, and we aren't there yet. So entanglement, we don't yet have an explanation for, and we may never, but the point is this is progressive, right? So we're thinking hard about it, and we're beginning to think that maybe it has to do with some sort of synchronization of the particles' clocks. But again, what's beautiful about this enterprise is it's progressive. So we aren't there yet, but we'll see if we get there. You're not going to get there unless you try. Okay, so big picture, just to close, how things looked before this hydrodynamic quantum system was discovered. You had classical mechanics and quantum mechanics, and it was sort of unclear how one passed from one to the other. But then we found this pilot wave system. Yves Couder discovered it, and we see that it classical mechanics is starting to intrude into quantum mechanics. And it also, so the theoretical modeling has inspired this generalized pilot wave framework, which allows us to capture more features of quantum mechanics. And finally, it's that one sort of end member of that generalized pilot wave framework is this hydrodynamic quantum field theory, where we can capture even more. So the question is, can we stamp out the yellow region entirely? And that's, of course, our modest goal. So this hydrodynamic system provides a vehicle for exploring the boundaries between classical and quantum systems. Certainly extends the range of classical systems to include certain quantum-like features. And we can see how, in particular, so the most important thing is it gives you a sort of physical framework for understanding certain features of quantum mechanics. So for example, how non-locality can be misinferred from a system which is local but hereditary. Okay, and we've seen how similar it is to de Broglie's original imagining. And also suggests the shortcomings, in my view, of the quantum pilot wave theories of de Broglie and Bohm. And again, we sort of have this fledgling hydrodynamic quantum field theory. I'm sure it'll have some problems, and we'll have to continue to revise and improve. But it's off to a good start. And for me, big picture, it suggests that the quantum paradoxes are ultimately going to be resolved through the elucidation of a pilot wave dynamics on the Compton scale. So as fluid mechanicians, we all know that, you know, D'Alembert's paradox lasted for 150 years, and it was only after it was resolved that modern fluid mechanics was born. Of course, itinerant with D'Alembert's paradox were many other paradoxes, but they all sort of went out the window as soon as they resolved the dynamics on the hitherto unimagined scale, which is that of the viscous boundary layer. So again, my suspicion is that something similar will happen in quantum mechanics once the Compton scale dynamics is resolved. So I'll end there, and if you want to learn any more, the recent review with Anand Oza was in Reports on Progress in Physics, and that's just out. So I'll welcome any questions. Thanks for your attention.
Thank you, John. Thank you for a marvelous talk. Very, very informative to catch up with all the recent work. So yes, we're open for questions. Any questions from anyone?
I would. Sorry, please.
Michele, yeah, go ahead.
First of all, thanks for the wonderful talk, and I have like 2 questions. From your system, can you somehow rederive an equation in terms of the phase and modulus of an associated wave function, like the classical quantum hydrodynamics that you presented at some point in your talk? And the other one, you just mentioned the viscous boundary layers. Have you thought of doing like a sort of shear flows instead of having like a Coriolis forcing term to somehow rotate just the boundary in your experiment to see what happens?
Yeah, we've been thinking about that in the context of Aharonov-Bohm. So, because there's a nice hydrodynamic analog of Aharonov-Bohm with water waves that Michael Berry did, with water waves sweeping over a vortex. So we've been thinking about precisely that. And it's very interesting in the context because, you know, I mentioned the particle interacting with a pillar, and that appears to be, it looks like it's interacting with the vortex, right? And so if you actually, so you can imagine that you could actually cloak the pillar, right? So if you rotate it to the right amount, you might actually be able to cloak it. So anyways, these are things that we're looking at, but it is shearing the interface is a very good idea and something that we're looking into. In terms of the first part of your question, no, we don't actually have a Schrodinger equation yet. So that's the point. We're sort of starting with the dynamics and then seeing what emerges. And we know that, so for example, in the Corral, the long time statistics converges to the Helmholtz equation, right? So as does the linear Schrodinger equation, but we haven't characterized the statistical relaxation to that state. So that's something we're also looking at. And we're, again, hoping to do this with using the sort of ensemble interpretation, where you start with a clump of initial conditions and look to see how they converge to the statistically steady state. But once we have that, then we can start thinking about how to mad along that and what we get. So yeah.
Yeah, no, because I think it will be kind of super interesting to see how how the potential is transformed in your set.
Right. Yeah, but I do think when we do that, I think the quantum potential will the role of that will be played by the mean pilot wave potential.
Mm. Thanks.
Okay.
Any other questions?
Okay, may I ask a question?
Yeah, of course.
Okay, so a very amazing talk. Just as you know, the talks I heard before given by you. Okay, so since this is quantum mechanics and the classical mechanics, so I will ask a very small question and then big one. Experiments that you said water droplets, so it's made of water, the same liquids, or it doesn't matter, does it?
Yeah, it's the same. It's the same. We use silicon oils. There are other, you can actually get water to bounce on water. Yeah, but it's the same fluid. It's one, it's fluid A on a bath of fluid A. Yeah.
Yeah. Does it
And
matter?
they don't coalesce. I didn't mention this, but they don't coalesce simply because there's an air layer between them, and that doesn't have time to drain during the impact time.
Okay. So there's nothing specific. You could have a silicone oil drop bounce on water or vice versa.
Yeah, you could, but yeah, if you do that, then after it coalesces, you have to change the bath, right?
Yeah. Okay. Okay. So
practical limitation.
so here, so who is helping who? So it seems quantum fluid mechanics is trying to help quantum mechanics. So that's okay. Are you going to answer this Einstein's question?
Well, we're hoping to, and we are getting some crossovers. So we have a sort of group which consists of mathematicians, engineers, and physicists. So we're all on the same side, trying to figure things out. It's sort of an engineering approach, which is, okay, can we do this? Did it? Okay, good, we can do that. Oh, we can't. Why didn't it work? And so it's sort of like this. It's a sort of progressive approach. So we know. So we've had many more successes than I thought we would have at the beginning. But there are still some. I mean, I can't see my way around entanglement right now. And there are even worse things. There's something called the quantum eraser, and this is mind-boggling. But again, but one has to. There are a number of the part of the problem when I studied quantum mechanics, anyways, that these things were all given equal weight in terms of things that you can't understand, and there are many things that you can understand from a sensible classical perspective, and it's just a question of pushing the boundaries between that which can be understood and can't, and that, after all, is what we should be doing as scientists.
Okay. What puzzles me, because quantum mechanics is all linear, and in classical mechanics, fluid dynamics in particular, everything is non-linear. So
right.
So this
so it's linear, but it's describing, but it's describing the statistics, right? So you can have. So what we're asking is whether a sort of complex, nonlinear dynamics with memory can give rise to linear statistics, right? And so that's really the question. So the dynamics is, of course, much more complicated than the statistics. Sure, you can solve. So, for example, like the Friedel oscillations, you solve Schrödinger's equation with some scattering potential and you're done. That's their entire description. But in order to describe the dynamics, it's very complicated. But we can do it and see that it works and gives rise to the same statistics.
Well, even at the statistical level, in microscopic level, you still have a lot of nonlinear stuff. So this kind of linearity in quantum mechanics is due to small scale, or what fundamentally why linear stuff works well.
I don't think it always does, right? I mean, and that's the other interesting thing, because we want to compare to systems where they've really done comprehensive experiments. So, for example, the Corral I like because I mean, to say that their description, they basically measure the the voltage within the Corral, and then they fit the resulting PDF with any number of modes. So their theory doesn't even tell you the weight of the modes, right? So they're just basically curve fitting. And so that's, that's entirely unsatisfactory for me. I mean, of course, one could do the same in our system, but it's really unsatisfactory. And there is a, nonlinear shorting equation and so forth. So there are limits to the linear description, even within their theory. But, the theory of, in terms of a theory of quantum dynamics, the best thing that they have so far is really Bohmian mechanics, but we can see what's problematic with that. In particular, it's non-locality, but I think it's becoming increasingly clear that the non-locality in Bohmian mechanics can be accounted for with hereditary mechanics and pilot wave mechanics.
Yeah, thank you.
So John, if you just a question on robustness, I guess, if you this Faraday wave that you set up, if you intentionally give it some stochastic noise, how would that affect the whole scenario?
So that's something that one could do, and you'd there be sort of perturbing, this, because this resonance condition is really key for the emergence of quantized states and so forth. But there is the possibility. I mean, it's sort of an interesting debate in the quantum literature whether the stochastic background, because some people just in stochastic electrodynamics, for example, they just appeal to stochastic background to excite the internal vibration of the particle, right? That's really all it is. And then it's you're off on a pilot wave theory. In other cases, it's this particle is vibrating, but also interacting with a stochastic background. So that actually plays a dynamical role. Whereas in the other one, it's just the stochastic background is just exciting the vibration of the particle. So that is a possibility in ours. I mean, I actually tend to think you'll just be smearing out a lot of the quantum behavior if we do that in the lab. So if we do apply a stochastic, notice that the stochastic element was appealed to in Bohm out of desperation, right? And we don't have such desperation. So let's do the simplest thing first, which is certainly not to introduce a stochastic background, but it might be interesting and it may be necessary, but we'll again try the easiest things first.
Yeah, or even, this other question about the shear, if you do the whole thing on a slightly inclined plane, I mean, of course, it's not easy, right? Because once it's gone, it's gone. But
yeah, we have been looking at actually weak slope. So there's some interesting things there because you can sort of, to a limited degree, model potentials using bottom topography. Of course, because the system has memory, it's not strictly true, but there, for example, you can get, if you have a conical base, you can stabilize circular orbits. So it looks like there's because the walkers, it turns out, always want to walk downhill, as you might expect on energetic grounds. But yeah, there's plenty to be done. And then, we'll move to more complicated things as necessary, but we'll see how far we can go with what we have. And I think, right now, I think the theoretical frontiers are very exciting. In particular, this generalized pilot wave framework as a means to bridge the hydrodynamic system and these quantum pilot wave systems, I think is quite promising.
Great. Yeah, thank you. Any questions?
Hi, Demetrius. I have a question.
Yes, Ori.
John. So my question is about how robust the phenomena that you're describing are with respect to the mechanics underlying the phenomena. So it seems like the basic ingredient is that you have a resonance or some sort of instability, more general, and that's attached to a disturbance that's been created by that resonance or by the particle. But you can think of other analogous systems which would produce, in particular, a different kernel in your memory interval.
Sure.
So instead of a Bessel function, you would have something. So what I have in mind specifically is a particle which is creating a disturbance of solute, and then the solute can become asymmetric, and that asymmetry would result in particle motion. So these are
As you said, a solid, you say, a particle interacting with a solid?
no, a particle generating solid concentration.
Oh, okay, okay.
And there is some instability, and that instability results in a gradient of the solute, and that results in particle motion. So these are these so-called active particles. And then you have a system where you have when you include advection in that system, you have an instability, and the particles can spontaneously move, sort of analogous to the walkers that you described. And then you have a system where you have this instability, and the particle is generating its own disturbance, but the disturbance is not governed by a wave equation, but by an advection diffusion equation. And you can also write this sort of model down, and you have, well, you don't have inertia in that case. That's a big difference. But you have a particle moving under the influence of its own solid distribution, which is influenced by a memory effect.
Yeah,
So,
I can imagine how that would work, but is it pulsatile? Because I mean, is it emitting this solute in a periodic fashion?
it's not, but I still feel that there is an analogy.
I think you would need to, yeah. And because so there are, so
But
I
there
should
is a
say
time
that,
scale, John.
Yeah.
There is a time scale.
because I can imagine that, because I mean, that's not so far from acoustic waves. And this is something that someone has been trying to do, is to get, so a 3D pilot wave system, you can imagine exciting a bubble acoustically. And so it's basically emitting radially symmetric waves. And then it becomes unstable at a certain stage and starts moving. That's sort of the physical picture we have as we're developing this 3D generalized pilot wave framework. There are also people, so Christian Borghese and also a group in France led by Aurélien Drezé, they're looking at basically a particle interacting with a elastic substrate. So there again, but in all of these, the key thing is that the particle has to be vibrating. I think with your solute, with your chemical pilot wave system, the thing would have to be emitting periodically, and you'd have to have some resonance condition, because again, it has to move in such a way that after each cycle, it's sitting on the same gradient, right? That's kind of the key in all of these pilot wave systems.
Yes, but you do have an instability here, which allows the particle to move spontaneously without any external forces. So in that
Right,
sense,
true, true. But it's, again, it's got to be periodic. So I just can't, if the thing's just emitting chemical gradient, I don't see how you're going to get a resonance condition or quantization for that matter.
you get an instability, which is
Yeah, you could, yeah. But the key, like the quantum-like features are rooted in this fact that it's carving out this monochromatic potential, right? So you could do that with chemicals if it's sort of emitting periodically, I think, but otherwise not.
okay.
Okay.
Yeah.
Okay, if I may I ask them?
Please.
Question.
Yeah, who's?
Go ahead, it's all right.
Sorry. Okay, so for Faraday, you have imposed the acceleration. It seems to me a few other experiments, you don't have any imposed field, so to speak, acceleration or gravity wave. So the acceleration is self-induced by the particle. Is that right?
Yeah, that's right. That's right. And in fact, it's funny you mentioned gravity waves, because that's the other thing. Because from my perspective, any pilot wave will do. We're in the hydrodynamic quantum field theory. We're trying to model these matter waves in terms of the Higgs field. So because it's simple mathematically, but there's also the possibility of electromagnetic fields, and this is something that De La Peña and Cheto have looked at. And there's also gravity waves. And I've been getting bombarded with emails saying, you got to look to gravity waves as your pilot wave. But whenever I look at the mathematical formalism of GR, I find myself scurrying with my tail between my legs. But it is certainly a very interesting direction to explore, because after all, the sort of physical picture of a particle vibrating, exchanging rest mass energy with field energy, it sounds like gravity waves might be the best candidate.
Okay, thank you.
I have a question regarding the Faraday waves. It is true that the most, I mean, the response in Faraday waves, usually it's subharmonic. That means you
Right.
vibrate twice and it's oscillate once. But there are some experiments they managed to excite like this, like the harmonic.
That's right. Yeah.
Are we able to have the same bouncing if the response is harmonic?
So you would get, that's a good question, and I've thought about that myself. So you would get the bouncing state. You could definitely get the bouncing. It's not clear whether you could get walking. So the walking, it turns out, I think it probably, I suspect it would be even easier to get walkers, because in our system, initially they're bouncing with the driving frequency. Sort of what do you expect? And it's only when you increase the amplitude of the driving, then you get a period doubling, and then you achieve resonance between the bouncing drop and the wave, and that's when it starts walking, right? So if you had, if you were in the regime where the most unstable Faraday wave is harmonic, it would probably be easier to get them to walk. But you know, that would mean digging around for the appropriate fluid and parameter regime, and it's the fact that it's harmonic, subharmonic rather than harmonic doesn't really affect things at the end once you're onto the pilot wave system. But it's kind of a good idea, and I'm sure there's been a lot of stuff done. There's a group in Australia led by Tapio Simula, and they've been looking, found a sort of new parameter regime where they get so-called super walkers, and these are drops which are 5 times bigger than, and they travel 5 times faster, and so there are all sorts of possibilities, and also different resonances, right? So it doesn't have to, you can have, the drop itself is an oscillator, so there's one frequency, there's the bouncing frequency, and there's a wave frequency, and in our system, all 3 are synchronized, but if you change the relative magnitudes, you can still have higher periodicities. So for example, if you have excite a higher mode of oscillation of the drop, you can get tumbling motion. This is work that Tristan Gillet did. And so there are all sorts of, so you basically have 3 frequencies, and you're going to get different physics according to the different resonances excited.
So you're saying, John, it wouldn't work for a solid sphere?
No, so in fact, it should. We actually tried it. It was, so the reason you'd have to have a really smooth sphere, because if you have any roughness on the sphere, it'll sort of puncture the lubrication layer of air and then make contact. And that was the problem we were having. I think if you took a sphere and you coated it in fluid, because if you have a liquid, then it's going to be smooth down to the molecular scale, right? So, but in principle, you should be able to get solid things to walk. But we have, excellent, yeah. So there are, and actually, so Dan Harris did something very interesting recently in Brown, which is he has these floating objects, and they actually don't lift off. But so he just vibrates the bath, and these things generate waves and basically go unstable on their own wave. So they actually self-propel like walkers, but they actually don't detach from the interface. So this sort of discontinuity between the particle and the wave is not necessary, which is of course just as well when you move to 3D, right? Because right.
Yeah, very good. Yeah. Any other questions?
Just you showed many animation where you have many droplets.
Yeah.
So I know that I saw one day if Couder was taking like a pinch on the liquid and then he did it. But when you have a lot of droplets, do you have like an airbrush or I mean to
generate them?
Yeah.
Yeah. So he used a toothpick. We took it to the next level, and we have a drop generator which produces drops of identical size. So it was something developed by Dan Harris, and that's kind of key. So they were as skillful as you could be with a toothpick, but you can see just looking at some of their figures of their lattices, the drops aren't actually of uniform size. So in terms of looking at stability of these lattices, you kind of want to make the size uniform, and we can do that experimentally now.
John, can I just ask another quick question, please?
Sure.
So in the videos, it seems like the drops are typically 1 millimeter, as you mentioned. What's the importance of the bond number? What did you investigate?
So Yeah, so the bond number, of course, prescribes relative importance of gravity and surface tension, and it's small in this system. So basically, because the bond number is small, the interface behaves effectively like a linear spring. So it's a linear spring whose spring constant is proportional to the surface tension. So if you just calculate the surface energy associated with a small distortion of a planar interface by a sphere, you'll see that the surface energy increases linearly. The energy goes up like penetration depth squared, so the force goes linearly. Yeah. So in any case, yeah, behaves like a linear spring where the spring constant is effectively surface tension. So gravity's out the door. You know, one place that gravity comes in, which is kind of interesting, is in the breaking of the interface. So in quantum mechanics, they talk about the Compton scales, the scale of spontaneous particle, antiparticle creation. And of course, if we shake the bath really hard, drops, you know, the interface breaks and you create drops. And we're looking at this as a sort of model of super radiance now, but in the absence of gravity, you would actually get bubbles forming beneath the interface, drops forming above it. So there we would have our particle, antiparticle. So gravity is basically breaking the symmetry of the system, right?
Right. But if you have larger drops, they just don't.
Yeah. So there's a small parameter regime in which they walk, and it's the key is the sort of resonance between this frequency, and the wave frequency.
Okay.
If you put larger drops there, they'll just sort of hover and eventually coalesce.
Okay, thanks.
Great. Okay, let me